Stars are luminous globes of gas, in which the inward pull of gravity matches the outward push of pressure. The nuclear energy released in the interior at high temperatures is radiated from the surface at low temperatures, and this low-temperature radiation sustains the chemistry of planetary life. But to each star comes a day of reckoning. Its central reservoir of hydrogen approaches exhaustion, and the star begins to die. The tireless pull of gravity causes the central regions to contract to higher densities and temperatures. And, as a consequence, the outer areas swell up, and the star becomes a red giant. A star like the Sun then evolves into a white dwarf in which most of its matter is compressed into a sphere roughly the size of Earth. Many stars end as white dwarfs, slowly cooling, supported internally against gravity by the pressure of electron waves, as in ordinary metals, more massive easily. Gravity is stronger in these stars, and their central regions continue to contract to even higher densities and temperatures, thus enabling them to draw on the last reserves of nuclear energy. These stars become luminous giants, squandering energy at a prodigious rate. Soon, their reserves of atomic energy are exhausted. Only gravitational energy remains with its fatal price of continual contraction. In their final throes, the cores rush inward, the mantles explode outward, and for a brief, ecstatic moment, these stars become blazing supernovas. Out of these cataclysms are born neutron stars in the form of rapidly rotating pulsars. The most massive stars have imploding cores that any known state of matter cannot arrest. Gravity, usually the weakest of forces, overwhelms all opposition, and the end is the birth of a black hole. If we fall with the imploding core of a massive star following its final moments, in tens of microseconds, the core hits virtually infinite density. It becomes a singularity, in some ways similar to the extremely early universe, about which we still understand very little. The only surviving particles under these extreme conditions are perhaps the fundamental quanta of spacetime. Spacetime itself is a dense foam, in which space and time are inextricably scrambled together, and an orderly, time-like sequence of events vanishes. But to a distant observer in the outside world, the falling star never reaches the singular state. The gravitational redshift steadily increases, and the star appears to fall more and more slowly. As the star approaches a critical size, known as the Schwarzschild radius, the redshift approaches infinity. The star reddens, darkens quickly into blackness, and stays forever in the crucial size, frozen in a permanent state of free-fall collapse. Nothing, not even light, can now escape to the outside world, according to classical theory. Within the collapsing star itself, doom lies only a fraction of a second away. To a distant observer, however, the star is a black hole where time stands still, and the fate of gravitational collapse is forever concealed from view. Let observer A fall into a black hole and observer B be far away in the outside world. B thinks, why should I worry about the fate of A? In my space and time, A is suspended forever in a frozen state and will never reach the singularity. But is this true? Theory shows that in a closed universe of normal pressure and density, there is only one future singularity. The observer in the collapsing star sees the outside world blue, shifted, and the blue shift attains its extreme value when the star reaches the critical size, the Schwarzschild radius, and becomes a black hole. Everything in the outside world is seen sped up by observer A, getting faster and faster as the collapse progresses, and at the critical size, he sees that everything outside happens with extreme rapidity. The future history of the universe passes in a flash. Suppose that in the far future, in tens or hundreds of billions of years in our time, B's time, the universe ceases to expand and collapses back into a second Big Bang. The inside observer A sees all this happen in little or no time. The galaxies streak away and then streak back again, and the outside world soars in density until it matches the density of the black hole. Time inside the black hole and time in the outside world now tick away together at the same rate, and A and B, holding hands, descend together into a cosmic singularity. Observer B outside, who congratulates herself on not falling into the black hole, now finds herself on equal footing with the inside observer A. And together they meet their doom. Binary systems. Most massive stars are members of binary systems. We saw that stellar evolution in close binary systems is complicated by the exchange of matter from star to star. When star X in a close binary system swells into a red giant, it spills matter onto its companion star Y. Then, with reduced mass, X evolves into a neutron star, or perhaps a black hole. The companion star Y, in turn, swells up and returns matter to the collapsed star X, which grows in mass, and, if it is a neutron star, might implode and become a black hole. The companion star Y continues to evolve and finally collapses into either a neutron star or a black hole. The most massive stars are 50 or more times the mass of the Sun. And it is therefore difficult to escape the conclusion that many stars, either isolated or in binary systems, have evolved into black holes. Collapsed stars in binary systems are of interest to astronomers. The gas from a companion star that spills over and falls onto a neutron star or a black hole is heated and radiates considerable energy as X-rays. Numerous X-ray sources are known to be binary systems, and in each case one of the companions is either a neutron star or a black hole. Neutron stars have masses usually less than 3 solar masses, and collapsed stars of greater mass are probably black holes. A candidate for a black hole is the collapsed star in the X-ray binary source known as Cygnus X1. It was the first X-ray source discovered in the constellation Cygnus, and the collapsed star has a mass approximately 8 times that of the Sun. Curved spacetime of black holes. John Mitchell and Pierre de Laplace demonstrated in the late 18th century that Newtonian theory predicts a significant event occurs when the escape speed from the surface of a body equals the speed of light. According to general relativity, spacetime is curved by matter, and the curvature is a measure of the strength of gravity. When a body of fixed mass contracts, its surface gravity increases and spacetime becomes more curved. At a critical size, known as the Schwarzschild radius, spacetime becomes so curved that, in effect, it entirely encloses the body. The body has become a black hole, wrapped in curved spacetime, and nothing, not even light, can leave it and escape to the outside world. A stretched horizontal rubber sheet helps us to visualize what happens. We imagine a ball slowly shrinks. While we watch the ball on the rubber sheet shrink, we notice how the sheet becomes more depressed and curved in the central region. Eventually, when the imaginary ball is tiny and very dense, the sheet enfolds the ball, except for a narrow connecting neck. The ball is not completely isolated because of the neck connecting it with the rest of the sheet. A black hole is also not entirely isolated because it is associated with the outside world. The amount of depression in the sheet at a fixed distance from the ball is determined by the ball's mass, and because it is fixed, the curvature of the sheet remains unchanged while the ball shrinks. This effect is similar in general relativity. At a fixed distance, the gravitational field, or curvature of space, remains unchanged as a spherical body of fixed mass contracts. The curvature of space remains unchanged, and hence no gravitational disturbances travel away from a collapsing spherical body, the Schwarzschild radius of a black hole. The Earth's mass is about 1 centimeter. If the Sun collapses to a sphere of 3 kilometers radius, or the Earth collapses to a sphere slightly smaller than a table tennis ball, both would become black holes and have infinite redshifts. Redshift. Rays of light leaving a luminous gravitating body are affected in two ways. They are redshifted and deflected. As a spherical body of fixed mass contracts, its surface gravity increases in strength, and light rays emitted from the surface are increasingly redshifted and deflected. Let r be the radius of a body whose Schwarzschild radius is rs. Light deflection. Light rays moving tangentially to the surface are deflected the most. Again, we imagine a contracting spherical body of fixed mass. When the contracting body reaches a radius 1.5 times the Schwarzschild radius, all rays emitted tangentially to the surface are curved into circular orbits. Only the rays emitted within an exit cone can escape, and this exit cone narrows as contraction continues. When the body reaches the Schwarzschild radius, the exit cone closes completely, and no light rays escape. Redshift and deflection conspire to ensure that no radiation escapes from a black hole. The photon is the surface where light rays can travel in circular orbits around a black hole. Again, we consider what happens at the surface of a contracting spherical body, and this time, we imagine that particles having rest mass are shot out horizontally from a point on the surface. Usually, we can find a velocity such that a particle will follow a circular orbit. Particles in circular orbits still obey Kepler's law. P2 is proportional to R3 in general relativity, provided that the period p and the orbit radius r are measured in the space and time of a distant stationary observer. Circular orbits, however, are not possible when the radius is less than 3 times the Schwarzschild value, and particles within this region spiral inward and are captured by the black hole. Light cone tilting. Gravity is weak at large distances from a black hole, and spacetime is approximately flat and the same as the spacetime used in special relativity. But close to a black hole, spacetime is significantly deformed. The intervals of space and time distant observer. It is more convenient in terms of the normal space and time of the distant observer. When we say that a black hole has a certain radius, such as 3 or 30, not the space of a nearby observer, but that of a distant observer. Let us consider a particle falling toward a black hole in terms of the space and time of a distant stationary observer. At large distances from the black hole, the particle has light cones similar to those of the distant observer. As the particle approaches the black hole, its light cones become tilted, and its future light tips forward toward the black hole. The curvature of spacetime causes this tilting of the light. When the particle reaches the Schwarzschild surface, its future light is tipped so far forward that all light emitted by the particle falls into the black hole, and none escapes to the outer world. The past light is tipped so far backwards that light is received only from the outside world, and the particle, therefore, sees only the world it leaves and not the fate that awaits it. Inside the Schwarzschild surface, the light cones are tilted even more. All light emitted by the particle moves ahead into the singularity, and the particle cannot see the singularity into which it is plummeting. The free-falling particle's spacetime, in its immediate vicinity, is flat, and the same as that of ordinary special relativity. Thus, the particle passes smoothly into the black hole without knowing that something terrible has happened. In its own time, it reaches the singularity in a time equal to the Schwarzschild radius divided by the speed of light. To the distant observer, however, it takes an infinite time for the particle to reach and enter the black hole. The point circle survey. Emitting points and wavefront circles help us to understand the effect of spacetime curvature. We imagine that a point in space, stationary relative to the black hole, emits a brief pulse of radiation. The wavefront circle shows us where the rays of radiation have reached a moment later. Far from the black hole, space is of the wavefront circle. Near the black hole, the emitting point is off-center and displaced away from the black hole. Curved space shifts the wave-front circle. In effect, gravity drags the light rays toward regions of stronger gravity. Dynamic space. This dragging effect is the same as if space itself flows into the black hole and carries the light rays with it. That space is dynamic, forms an essential part of general relativity, and is of utmost significance in cosmology. It will be encountered later in the expanding space paradigm. Special relativity tells us that nothing moves through space faster than light. General relativity agrees, but tells us that space, being dynamic, may also move, and its motion is not subject to the rules of special relativity. In some instances, as inside a black hole and outside the Hubble sphere, space flows faster than the speed of light. At the Schwarzschild surface, the emitting point is located on the wavefront circle itself, just what one would expect with space itself, flowing inward at the speed of light. Light rays moving outward at the Schwarzschild surface remain in the same place. They move at the speed of light and travel through space that is itself falling in at the speed of light. The surface of the black hole is the country of the Red Queen, where one must move as fast as possible to remain in the same spot. The event horizon. The surface of a black hole, where space in effect falls inward at the speed of light, is known as the event horizon. Events inside the horizon are unobservable and can never communicate with observers outside, because light signals cannot travel faster than the speed of light. A signal, the event horizon. Inside the horizon, space flows inward quicker than the speed of light, and outward-moving signals traveling through space at the speed of light are dragged inward and cannot reach the horizon. Special relativity is still valid locally in the frame of the free-falling particle. And in this free-falling frame, the local speed of light is the same as that used by the distant observer in flat space. Free-falling observers who use special relativity locally are carried along in the flow of space. A spaceship that falls into a black hole can never escape its doom. No matter how strong the thrust of its rocket engines, the spacecraft cannot exceed the speed of light in its own local space, which is itself falling faster than the speed of light. Perfect symmetry. Non-rotating black holes are perfectly spherical. This raises an interesting question. If the collapsing body is not exactly spherical, does this mean the final black hole is also not exactly spherical? Number. During the final moments of collapse, all non-spherical irregularities are radiated away into the outside world as gravitational and electromagnetic waves, leaving behind a perfectly spherical black hole. This is quaintly referred to by the phrase, "black holes have no hair." Long-range fields of force, such as gravitational and electric fields, survive the collapse. Still, non-radial short-range fields of force, such as magnetic fields, are either pulled in or radiated away. If nothing can escape, it has been asked, how is it possible for gravity to reach out beyond a black hole? A way of looking at this question is to think of gravity as radial lines of force. The collapsing body slides down the lines of force, leaving it to survive in the outside world. Another and better way is to understand that gravity consists of curved spacetime, which is continuous and cannot terminate at an edge. A black hole is not an isolated universe of its own, but remains connected with and part of our universe. Rotating black holes. Up until now, we have considered black holes as having mass and nothing else. More generally, three basic quantities determine a black hole: mass, rotation, or rather angular momentum, and electric charge. These are the only properties that survive when a collapsing body becomes a black hole. Substantial concentrations of electric charge are rare in astronomy, because they are easily neutralized by electrically charged particles in the interstellar medium. And most massive bodies tend to be electrically neutral. We shall therefore not explore the effect of electric charge in black holes. Rotation, however, is standard in astronomy and cannot be ignored. Almost all matter in the universe exhibits significant scale bulk rotation. Stars generally rotate, and as they contract, they spin faster. Most stars would fly apart due to centrifugal force long before they had contracted to the size of a black hole. However, stars in their final stages employ various strategies to counteract the rapid rotation of their contracting cores. The neutrinos that stream out of the core carry away some rotation, angular momentum, and the spinning core is also braked by viscous forces and magnetic fields that link it with the slower rotating mantle. Through various means, the core sheds its rapid rotation and continues to collapse, eventually becoming a neutron star or even a black hole. There is little doubt that neutron stars and black holes are generally born with rapid rotation, and some initially may spin at 10,000 revolutions a second. The gas dispersed between stars is generally in a swirling state of motion and cannot fall from large distances directly into a black hole. Gas, instead, will accumulate around a black hole and rotate in the form of a disk-shaped cloud. Such a rotating cloud, called an accretion disk, is supported against gravity by centrifugal force, just like the rings of Saturn. The inner regions of the disk, by Kepler's third law, revolve around the black hole more rapidly than the outer regions. Friction within the disk breaks the inner areas and speeds up the outer regions. As a result, matter in the inner areas of the disk loses rotation and slowly spirals inward until it is accreted by the black hole. And matter in the outer regions gains rotation and slowly spirals outward, carrying away into space excess angular momentum. The accretion disk is continually replenished with gas falling in from considerable distances. Even if a black hole initially had no rotation, it would soon acquire rotation from the accretion of swirling gas. Accretion disks develop in regions where an abundance of gas exists, such as close binary systems and the nuclei of galaxies. The Kerr metric. Carl Schwarzschild in 1916 solved the Einstein equation for the exterior spacetime of a non-rotating black hole. Roy Kerr in 1963, the year that quasars were discovered, solved the Einstein equation for the exterior spacetime of a rotating black hole. The Kerr spacetime, or Kerr metric, is not as simple as the Schwarzschild spacetime. In the discussion of non-rotating black holes, we saw that spacetime curvature causes the future light cone to be tilted in the direction of the black hole. Now, in the neighborhood of a rotating black hole, we have the additional effect that spacetime curvature causes the future light to tilt also in the direction of rotation. We have previously imagined space flowing into a non-rotating black hole, creating an event horizon at the Schwarzschild radius, where space flows inward at the speed of light. We must now imagine that space also rotates like a whirlpool as it flows a rotating black hole. Particles caught in the whirlpool are carried around as they fall inward. We can visualize what happens more easily by using emitting points and wavefront circles at large distances from a rotating black hole, as well as the space of the wavefront circle. Near the black hole, the rays emitted by the point are dragged inward and around, and consequently the wavefront circle is displaced partly in the inward direction and partly in the direction of rotation. This situation for the first surface, known as the static limit surface, or just the static surface, is where space flows at the speed of light. At this surface, the static emitting points are at the edges of their wavefront circles. The second surface is the event horizon, where space flows in the inward radial direction at the speed of light. At this surface, all emitting points and their wavefront circles touch the horizon. The outer static surface has the shape of an oblate, flattened spheroid, as in figure 13.12, and an equatorial radius equal to the Schwarzschild radius. It is the surface where space flows at the speed of light, and a particle, stationary in this flow of space, is dragged along at the speed of light relative to the distant observer. If the particle moves against the flow of space at the speed of light, it remains static on this surface. Hence, the name static surface. The wavefront circle protrudes outside the static circle, and some rays of light can therefore still escape to infinity. Inside the static surface, space flows faster than light, and a particle, no matter how fast it moves against the flow, is constantly dragged along and can never be stationary relative to the distant observer. The inner surface, the event horizon, is spherical. Across this surface, space moves inward with a radial component of velocity that equals the speed of light. Light rays traveling in any direction cannot escape the outside world. Both surfaces, the static surface and the event horizon, are in contact at the poles. In a non-rotating black hole, both surfaces merge and have the Schwarzschild spherical configuration. As rotation increases, the event horizon shrinks to a smaller radius, and at maximum rotation has a radius half the Schwarzschild value. At maximum rotation, on the equator of the event horizon, it rotates at the speed of light relative to the distant observer. The ergosphere. Between the event horizon and the static surface lies a region known as the ergosphere. It consists of swirling space, spiraling inward to the horizon. See Figure 13.13. Space in the ergosphere flows faster than the speed of light, but the inward radial component of the velocity of the flow is less than the speed of light. Static points lie outside their wavefront circles, but some rays can still move outward and escape to the outside world. Roger Penrose of Birkbeck College, London, showed that, in principle, it is possible to gain energy in the ergosphere from the black hole. A body is shot into the ergosphere, where it divides into two components. One component is shot backwards against the rotation, and the other component moves forward with increased energy. The first component plunges into the event horizon, and the second component escapes across the static surface, carrying energy that comes from the rotational energy of the black hole. Some of the mass of the black hole is due solely to its rotational energy. A black hole in which naked singularities are typical, but the eruption of energy from such singularities might be so enormous that life could not exist in these scorched universes. We exist because naked singularities do not exist, and the cosmic censorship hypothesis conforms with the anthropic principle. Once born, a black hole grows by accretion to Brobdingnagian size, and the rotational energy contributes to its growth of 0.29 of its mass, and is the maximum amount of mass that can be extracted as energy by the Penrose method. Robert Wald in Space, Time and Gravity cautions us with these words. The energy extraction idea discussed here, as well as all the other ideas in this book, is, at least at present, of interest for understanding nature rather than for possible practical technological advances. At maximum rotation, the event horizon has a radius half the Schwarzschild value. Its surface at the equator rotates at the speed of light, and space falls inward at the speed of light. Suppose that it was possible to increase the rotation even further. The horizon would vanish. In effect, the rotational velocity would increase, but the inward velocity of flowing space would decrease and be less than the velocity of light. Radiation would then escape, and the singularity would become exposed to the outside world. Penrose's cosmic censorship hypothesis has ruled out the concept of naked singularities due to their alarming nature. Cosmic censorship states that all singularities are cloaked from view by event horizons, and natural laws conspire to avoid naked singularities. Universes exist in matter and become exhausted. In the nuclei of giant galaxies where stars and gas clouds abound, the possibilities are fantastic. Black holes draw in the gaseous wreckage of tidally disrupted stars, and black holes even swallow one another. They swell into supermassive holes of thousands, millions, and perhaps even billions of solar masses. The compressed and heated gas drawn in toward the black hole radiates energy. The radiated energy may be as high as 40% of the mass of the accreted gas. This conversion of mass into energy is significantly more efficient than the 1% conversion in nuclear reactions. The released energy covers a broad spectrum of optical, ultraviolet, and X-ray radiation, and may include infrared radiation from surrounding clouds of dust. Supermassive black holes of hundreds of millions of solar masses can grow over hundreds of millions of years in the matter-rich nuclei of giant galaxies, and while increasing, release energy at a prodigious rate. An accreting superhole can radiate more energy than an entire galaxy of luminous stars. The best buy theory of quasars is that they are accreting superholes, and possibly the powerful radio sources are driven by energy also released from superholes. The tidal forces of a black hole will tear apart a body, such as a planet or a star, when they are stronger than the gravity that holds the body together. As a rough guide, we may say that a body held together by its gravity will be tidally disrupted when its average density is less than the density of the black hole. The size of a black hole is proportional to its mass, and this means that its density is inversely proportional to the square of its mass. The gas, compressed as it drains inward, radiates energy efficiently. But when the mass has grown to the point where the tidal disruption of stars ceases and the black hole swallows whole, the energy output wanes. Stars, approaching black holes of mass greater than 10 to the power of 8 solar masses, survive tidal disruption and dive straight in without releasing very much energy. A spaceship could plunge into a supermassive black hole of millions of solar masses without its human occupants experiencing significant discomfort from tidal forces. In the case of a superhole of much greater mass, the occupants at first might not even know that they had passed the event horizon. All black holes so far discussed have masses greater than that of the Sun, and it is unlikely that Lilliputian black holes of lesser mass are ever produced by gravitational collapse. A planet, such as the Earth, for example, can never collapse and become a black hole because gravity in these smaller bodies is not strong enough to overcome pressure gradient forces exerted by matter. Yet conceivably, black holes of a wide range of masses were once created in the early universe. In the early stages of expansion, the density of the universe was extremely high, and cosmologists had conjectured that black holes might have formed when their densities were comparable to the density of the universe. Various speculative ideas have emerged that involve black holes. One idea is the time-reversed black hole. It has been suggested that a collapsing black hole can be reversed to make a white hole, in which everything rushes out in an immense release of energy. This theory gained popularity in astronomical circles during the 1970s. What happens when matter falls into a singularity? One answer, some said, is that it emerges elsewhere in the universe as a white hole at a different place and time, or perhaps even in another universe. Black holes in other universes possessing equal rights pop out unexpectedly in our universe as white hole eruptions. One bold suggestion was that matter is siphoned from black holes back into the Big Bang, which is hot because the matter reappears as white holes. There is no evidence that matter can be transported in this manner, and the concept of white holes no longer seems tenable. There is also the argument that black holes form bridges connecting widely separated regions of spacetime. Such bridges, sometimes called wormholes, are supposedly used by technologically advanced civilizations as a transportation system for faster-than-light space travel and backwards and forward travel in time. The idea of using bridges as time machines has drawn attention in recent years, particularly in the entertainment industry. A time traveler journeys almost instantaneously to a space station at distance L that recedes at velocity phi. The time traveler then returns almost instantaneously via a second bridge and arrives back on Earth in the past, at 55 units of time preceding departure. If the space station is approaching at velocity 5, the time traveler arrives at 55 units of time in the future. The construction of bridges that remain open and are suitable for transport requires a source of exotic matter with positive density and negative pressure. That black holes are the birthplaces of offspring universes is yet another suggestion. Black hole singularities likely resemble the cosmogenic foam found in the extremely early universe. The suggestion is that each black hole collapses into a singularity that then inflates to form a new or offspring universe. Black holes in the offspring universe give birth to further universes, which in turn give birth to more universes, and so on. Lee Smolin of Syracuse University proposed that this reproduction of universes forms the basis of a natural selection theory that explains why the constants of nature, the gravitational constant g, the speed of light c, the Planck constant h, the electric charge of the electron, and the subatomic masses, have their finely tuned values. The anthropic principle states that the constants are compatible with our existence and are necessarily finely tuned. Smolin's natural selection theory suggests that the constants are finely tuned because black holes exist, and black holes imply the existence of stars, which in turn indicate the existence of planets, and ultimately, the existence of life and human beings. In 1974, Stephen Hawking, then at Cambridge University, demonstrated that black holes emit thermal radiation. This remarkable discovery revealed that black holes are less black than previously supposed. To understand why black holes radiate, we must examine the nature of space. The vacuum is not as empty as we might think. It is a dense sea of virtual particles of every kind, each existing for only a fleeting moment. According to the uncertainty principle, energy may always be borrowed but must be repaid within a limited time. The greater the amount borrowed, the quicker it must be repaid. For example, the energy needed to create 2 electrons, one positive and the other negative, can be borrowed for 10 to the power of negative 21 seconds. And for 2 nucleons, the repayment time limit is 10 to the power of negative 24 seconds. The whole of space is filled with virtual particles that incessantly appear on borrowed energy and then disappear when payment is due. Collectively, they account for many observed effects in the structure of atoms. Yet each does not exist long enough to produce its gravitational field. Subatomic particles are more than just packets of energy. They possess conserved quantities, such as spin and electric charge, that cannot be altered. Virtual particles are, therefore, always accompanied by their antiparticles. A virtual electron has a negative electric charge and is accompanied by a virtual positron, which has a positive charge and is the antiparticle of the electron. A particle spins in one direction and its antiparticle spins in the opposite direction, and their combined spin is 0. The vacuum is densely populated with virtual electron pairs, electrons and positrons, whose combined spin and electric charge are 0. Particles and antiparticles have the same mass, but their conserved quantities are always the opposite of each other. Thus, when a particle and its antiparticle appear briefly in a virtual state, only their joint energy has been borrowed. Photons, particles of quantized radiation, are their antiparticles. The antiparticle of a photon is another photon of opposite spin. Both kinds are equally abundant and are emitted equally by non-rotating luminous bodies. Luminous bodies of either matter or antimatter emit similar photons. The vacuum seethes with virtual photons in addition to all other virtual particles. Whenever a virtual particle and its antiparticle can gain sufficient energy to become real, they do not return to the limbo of the vacuum state. Various methods can be used to achieve the required energy. We discuss two methods. Consider an electric field between two parallel conducting plates. Increasing the potential difference between the two plates increases the strength of the electric field in the space between the hordes of virtual particle pairs, including electron pairs, each existing for only a brief moment. During the short existence of a virtual electron pair, the electron is attracted to the positive plate, and the positron is attracted to the negative plate. Usually, in their short lifetime, they move apart hardly at all because the electric field is too weak. But when the electric field is strong, approaching 116 volts per centimeter, the oppositely charged electron and positron move apart a sufficient distance to gain from the electric field the requisite energy to become real. The vacuum now springs to life, and a deluge of electrons, positrons, and photons is created. Stronger fields create heavier particles. Gravitational fields. Consider now virtual particles in a gravitational field. Particle pairs are accelerated in the same direction, but gravity tends to tear the pairs apart because of the tidal force. Black holes produce strong tidal forces, and the smaller the mass, and therefore size, of the black hole, the stronger the tidal force. When the tidal force near the surface is sufficiently strong, a virtual particle and its antiparticle are pulled apart to a sufficient distance, gaining the necessary energy to become real. Most of the fundamental particles created in this way fall inward, and no energy is lost from the black hole. But some virtual pairs separate sufficiently for one member to move outward, with enough energy to escape. Photons are also created in the same way from the vacuum state. Black holes, therefore, quantum mechanically emit particles, including photons and neutrinos, and continually lose energy. Particles, in their wave-like manner, penetrate seemingly impenetrable barriers. This behavior offers another way of looking at particle emission by black holes. A particle can tunnel through the event horizon and emerge as a wave. The most probable wavelength of the emerging particle is roughly the radius of the black hole. Hawking discovered that the emission of particles and photons is thermal, as a hot body. Black holes of solar mass have extremely low temperatures. The temperature is only 0.01 Kelvin. A black hole the size of a speck of dust with a radius of 10 to the power of -3 centimeters and 0.1 lunar masses has a temperature of 10 Kelvin. Mini-holes of atomic size have temperatures of 1 million degrees and emit intense radiation. Hawking's discovery has shown us that black holes are not black, but bright when small. They radiate energy and slowly lose mass. As their mass decreases, black holes get hotter and radiate faster. As a mini black hole diminishes in mass, its temperature and luminosity rise, and in its final moments, it erupts in an outburst of high-energy particles. Perhaps in the future, astronomers will discover these mini-hole outbursts. Black holes are heat engines. A black hole has mass, angular momentum, and electric charge, and nothing else. When a body falls into a black hole, it affects these three properties, and whatever else belongs to the falling body is forever lost. Each time a body falls into a black hole, a vast amount of information vanishes, never to be recovered. A black hole might form from matter or antimatter, or smaller black holes, or conceivably from radiation or gravitational waves. Over time, as photons. The black hole also emits neutrinos and other particles, such as electrons and positrons, and always equal numbers of particles and antiparticles are emitted. Its emission does not tell from what the black hole was made initially. It slowly evaporates, and even in its final outburst, it still emits equal numbers of particles and antiparticles. The emitted particles and antiparticles may then annihilate each other, producing further photons. It comes to this. A black hole is a machine for converting all forms of mass into radiation, and it has no memory of whether the mass was originally that of matter or antimatter. Except for mass, angular momentum, and electric charge, it ignores the conservation of things such as the lepton number. Black holes are heat engines that obey the laws of thermodynamics. They have temperature and therefore also have entropy. Entropy is a measure of information lost. It is also a measure of thermal disorder. In a closed and isolated system, entropy either remains constant or increases, but it never decreases. We can try to understand entropy by thinking of energy in all its many forms forever cascading into less practical and accessible states. In the process, entropy increases. For example, the energy from which it was formed, such as that from flowers, crystals, books, and planets, has vanished, and in return, it gives us photons of high entropy that lack order and information. The information lost to a black hole is proportional to the surface area of its event horizon. For a non-rotating black hole, this is equivalent to a burning candle, where the energy is converted into radiation, heat, and molecules in lower energy states, and entropy increases. When two black holes encounter each other and coalesce, they form a single black hole whose surface area is greater than the sum of the horizon areas of the two initial black holes. Yet we have that a black hole is hot and radiates away its mass. As its mass decreases, its surface area decreases, and its entropy, therefore, gets less. It does not violate the laws of black hole thermodynamics. The entropy of the black hole decreases because the emitted radiation carries away entropy into space. The closed system in which entropy is either constant or increases is not just the black hole by itself. Still, the whole universe, and, in the universe, the entropy of the black hole plus the entropy of the emitted radiation does not decrease. Black hole thermodynamics up a new realm of physics. Some astronomers have suggested that the galaxy contains billions of black holes. A black hole might, therefore, one day come our way, and the particles of our bodies, in company with the wreckage of the solar system, will be engulfed in a black hole. Instead of continuing to exist until the end of the universe, the particles, once engulfed, will exist for a fraction of a second in time before ending in the black hole singularity. However, suppose the universe comes to an end by eventually collapsing. In that case, all the particles in the universe, along with those that have previously fallen into black holes, will ultimately converge in the universal singularity. A black hole is a quick way to reach the end of the universe. The word antimatter was first coined in 1898 by the scientist Arthur Schuster in a letter to Nature entitled Potential Matter, a Holiday Dream. He discussed the possible properties of antimatter and speculated on the existence of antistars. He wrote, "Astronomy, the oldest and yet most juvenile of the sciences, may still have some surprises in store. May antimatter be commended to its care. Paul Dirac in 1930 developed a relativistic equation in quantum theory that revealed the possibility of anti-electrons and antiprotons. 2 years later, the positron was discovered, and the antiproton was found in 1955. Numerous subatomic particles and their antiparticles have been discovered with high-energy accelerators. Particles and antiparticles are distinguished by their conserved intrinsic properties, such as electric charge and baryon and lepton numbers. Baryons, for example, nucleons, protons and neutrons, are heavy particles. Their name derives from the Greek bari, meaning heavy. What is the universe? Antistars in antigalaxies emit the same. Most galaxies have unmistakable signs of their violent interactions. There are indications of violence, it is true, but not of the kind that emits gamma rays at distinctive energies. Gas dispersed between galaxies in the rich clusters appears not to contain an admixture of antigas because we have not observed the distinctive radiation that results from annihilation processes. The evidence so far indicates that antimatter is rare in the universe. According to grand unified theories, the universe is made only of matter because, in the very early expanding universe, the dominant hyperweak force distinguished